Okay, so now we're ready to look at bending of a symmetric laminate. And in the last section, we looked at the stress resultants, Nx, Ny, and Xy with in-plane loading, and came up with the extensional stiffness A that related the strains to those stress resultants. And we're going to do a similar thing now, again for a symmetric laminate subjected to pure bending. And again, it's got to be symmetric because when you do that, you can look at the extension and bending independently. There's no coupling between the two. Now, if you do have extensional loads, in-plane loads, and bending loads, you can actually look at those separately and just add the results using superposition. But when you get into non-symmetric laminates, it gets a lot more complicated, and we will look at that in section 7. But for now, again, we're sticking with symmetric laminates. So going back to our plate theory, and before we had the in-plane stress resultants in X, Ny, and Xy due to the stresses, sigma X, sigma Y, and tau 1, 2. Now we have a similar thing due to the distribution of those stresses. We have the moments m sub X, m sub Y, and due to the shear stresses, m sub Xy. Now, these are moments per unit width, just like n sub x was a force per unit width. So the units of these are going to be force times length divided by length. For example, in the unit system we're going to use exclusively, it's going to be inch-pounds per inch. So a moment in inch-pounds per unit width in inches. Now, one other thing about the nomenclature here, which is typical for plate and shell theory, m sub x, in statics you might have said that means the moment about the x-axis. That's not the case here. Rather, the moment m sub x is the resultant of the normal stresses in the x direction. So, make a couple of assumptions here. Again, we start out by saying, once again, the laminate has to be symmetric. That means that the midplane of bending, or the neutral axis, is going to be at the midplane. And a couple of other assumptions here, that same ones you made in mechanics and materials when you're looking at elementary beam theory. One of them is that there are no shear deformations, and so we normally say that plane sections of the beam remain plane. Same thing here with the plate. And we also say that the deflections are very small as well. So here's our plate. And again, the midplane of that, remember we are symmetric about that midplane. And let's take a piece out of that. And so here's the undeformed. We've got a line segment on the midplane. And we have another line segment that's below the midplane by a distance z. So we'll call that one AB. And the line segment that's on the midplane, which will be the neutral axis of bending, if you will, we'll call CD. So when we deform, when it bends, as we said, plane sections remain plane, and so that means we can look at projecting those plane sections up to a center of curvature, and that any line segment in here becomes a circular arc. And so there's our deformed line segments that are now become circular arcs, C prime D prime and A prime B prime. Now the radius of curvature to the midplane we're going to call rho. All right, so remember, as we said, CD is on the midplane, AB is Z below that midplane. And so when they're undeformed, they're equal to each other. But now when they're deformed, again, remember that that midplane is going to be the neutral axis of bending, so C prime D prime would have the same length as CD. And we can also say that it's a circular arc. So C prime D prime would be that radius of curvature rho times delta theta, the small angle. A prime B prime is also a circular arc, but now its radius of curvature is going to be a little bit more than rho. It's going to be rho plus whatever that z distance is that it is below the midplane. So now let's find the strain in segment AB. Okay, remember that for a small line segment we said the strain is change in length divided by the original length. So A prime B prime minus AB is the change in length, and the original length is just AB. But also remember this, AB is the same length as CD, and CD is the same length as C prime D prime. So we can write it like this, which allows us to write it in terms of the radius of curvature and the little angle. And you can see on top, we're going to have rho delta theta minus rho delta theta, so that cancels out. And so you end up with z delta theta over rho delta theta, and again the delta thetas cancel out, so just z over rho. And since the curvature is 1 over the radius of curvature, we can write this as the strain in the x direction is z times the curvature in the x direction. So obviously if z is equal to 0, there is no strain and you're on the midplane at that point. If you're below, which is positive z is below the neutral axis, that means it's going to be tension for positive values of moment, and compression for negative values of z, which would be the any distance above the midplane. So as we said, if we just have bending, the strain in the x direction is z times the curvature in the x direction. And as I mentioned earlier, although we're not going to look at that in this section, if you had in-plane loadings and bending on the same symmetric laminate, you could evaluate those separately and add the results together. And if you have bending in the other directions, then you have strain y and shear strain gamma xy associated with those curvatures as well. So it's kind of easy to picture, the curvature x. You think about a beam and how it bends. The y direction, yeah, if you're bending the other direction, the kappa xy, you can kind of think of that as being, I always use the analogy of a Pringles potato chip. If you kind of rotate it 45 degrees and the corners come up on opposite corners, and then the other corners are down. So that's due to the shear stresses. Tau xy creates that type of curvature. So with that in mind, we can now start thinking about how to relate the moment resultants themselves into the relate them to the strains, and then do the find the stresses from there as well. So just like we formed the extensional stiffness matrix A for in-plane loading, we're going to have a bending stiffness matrix that we call D.